some of these problems, starting at 2.2 on the bottom of page 2. It says as a train leaves a station, right? It says on there, I won't rewrite the problems. You might have done this one already. It says as a train leaves a station, 2.2 on the bottom of page 2. Why don't you number your pages? First page 1, flip it over, the back of the next page 2, then 3, 4, 5, etc., all the way up to 18 of 18, since I only labeled the last 2 pages on accident somehow. I don't know what happened. Yes. Your packet. Ooh. I didn't see one when I came back. I don't know if they put it somewhere. I have not seen it. Yes. That's topic 1. Well, I thought I did. Maybe I don't. I don't know. I mean, I can always print you out one, or you could print out a copy. It's just right now, I guess you'll just have to write it on paper. Okay? Oh, here it is. Not yours, but here's one of them. Okay, let's try again. Bottom of page 2, so you should have labeled your pages. Oh, you did. Okay. As a train leaves the station, it accelerates at 1.5 meters per second squared for 25 seconds. What is the final speed of the train? How far does it travel in that time? And so you've learned about the really good chart these days, right? And it looks sort of like that, and it has various things. So we have a train. Oh, that's a car. A train. And it's going down the track. It's leaving the station. We assume that it leaves at a speed of what? So what would that be represented as? Right, of 0 meters per second. Okay? And then it has an acceleration of 1.5 meters per second squared. It's going to go down the line whoops. Stop that. So it went down the line. Now it's moved. It's so fast you can still see it sort of over there. Now, time is 25 seconds to do that. That's a change in time. What is the final speed? That means VF is what we're looking for. How far does it travel? Oh, delta S as well. How far does it travel? Since it's only going in a straight line, the displacement and the distance traveled are the same. So as we fill this stuff in that we know, what's VI here? 0. What's VF? Well, we don't know it yet. But we do know A. And do we know delta T? So this is what we're going to work with. Okay, so I look at this and I can see that I can find VS because there's the equation, and again, you might want to put this one in your work of VF equals VI plus A delta T. So that equation means that your final speed is going to be based on the initial speed that you start with. What? Well, there's that one too. That's a different one. This one says that your final speed equals your initial speed that you start with. Paul, your initial speed that you start with plus your acceleration for some amount of time, right? If you start at 0 and you accelerate at 1.5 meters per second every second, well, let's say you only went 2 seconds. How much speed would you gain in those 2 seconds? 3 meters per second, 1.5 each second. So your initial speed plus the speed that you gain, that's what this gives you. So for us, VF would be 0 plus A, which is 1.5 meters per second squared, times 25 seconds. My pen's off a bit. So what does that give us? Now sometimes these work out nice whole numbers, and 37.5, not a whole number, but close. But if it doesn't, you don't have to think that that's wrong. What would be the units on that? Right, because a meter per second squared times a second is meter per second. So that gives us that. A meter per second squared times seconds is meters per second. Yes. Well, in this problem, yeah, fill it in. On a test, you could just get, if it doesn't say fill in the whole chart, you could just give me the information that's needed. It's possible, yeah. All right, so the average velocity, in this case, average velocity is, we could just do VI plus VF over 2. And since VI is 0, I get 37.5 meters per second divided by 2, right? What's the average of 6 and 8? 7, right? So it's 2 numbers divided by 2. And so that would give me 16.75? 18.75. Oh. So that would go here. Delta V is VF minus VI, so that would just be 37.5 since minus 0. So the one question was, what is VF? We answered that, didn't we? That's this. Oh, it turns black. See? Now, the last thing in there was delta S. What equation would I use to get delta S? Kayla? Okay, right. So if I use this and I bring that up, it's just average velocity times time, which is 18.75 meters per second times 25 seconds. The accelerating train $468.75. So 469 meters, right? That clear how to do that? Well, let's just aim around by the tenth unless that doesn't make sense. Like if you have 0.0025 seconds, right? Rounding to the tenth would not be a good idea. So there's a whole, the best way to round would be to put that in scientific notation, but I don't really want to focus on that right now. So delta V is VF minus VI. Remember, you can watch these videos at www.joshring.com anytime you want. There's other ones, too, that are longer, that are good for sleep and stuff. So I went to a sleep meditation workshop this weekend. It was quite nice. Yeah. Only for like an hour. She said though, if you do this, it counts for 3 hours of sleep. So I'll just do that. Well, it's all about like you have to like focus on parts, like each part of your body first, and then you imagine yourself through some sequences, and you go from moonlight to sunlight on a beach. Yeah, well, according to her, it accounts for 3 hours of sleep, so I'll just do that twice, and then I could do a bunch of work in the middle of the night. So it's good, though. You have to train yourself to sleep sometimes, right? Rest is important. All right. How about the bullet fired on the next page? So this bullet is fired into a thick block of wood. Okay, in comes the bullet, and it hits the block of wood. We'll make it green. No, it's the next page. The thickness of the wood is 0.1 meters, which is how much in centimeters? 10 centimeters, right? So it's about that thick. It goes right through it. And it goes through it and comes out the other side. Oops. Like that. You see? It's 0.1 meters thick. The bullet enters at 450. So VI is 450 meters per second. And then it says it exits at 350. So VF is 350 meters per second. So it goes through that block of wood and it slows down as it's going through. How long was the bullet in the block? Well, we'll get our really good chart out. And we'll go through it. We know VI was 450. We know VF was 350. and we know delta S was 0.1 meters. We don't know the rest. But very quickly we can get average velocity, because the average is just that, which would be 800 divided by 2, or 400 meters per second. Okay? So now we don't only know its initial velocity coming in and the final velocity coming out, but we know its average velocity, assuming that its acceleration was constant, which you do in these. The change in velocity is Vf, minus Vi, and Vf is 350, minus Vi, which is 450. What does that give me? Negative 100 meters per second. Why is it negative? Because what's happening? It's, slowing down. Can I get acceleration now? Well, it's delta V over delta T. I don't know delta T, but I think maybe all right, let's do it. V bar is delta S over delta T, right? So I can bring up delta T. So delta T would be delta S over V bar. Now delta S is 0.1 meters, and V bar is 400 meters per second, which would be 0.0025 seconds. I have it written down too. 3 zeros. Oh yeah, 0.1. So this is 0.00025 seconds. Why is my time so small? Does that make sense? It's a bullet through a piece of wood, right? So the time would be small. Now, I don't think it asks for the acceleration in this, does it? But we could get it. It's a deceleration. We're slowing down. My delta V over delta T minus 100 meters per second over delta T, which is negative 400,000 meters per second squared, or it slows down 400,000 meters per second every second. If it went a full second, well, that thing would have slowed down to 0 and be coming right back at you. Of course, it would probably just stop, wouldn't it? Or it would fall, because there's another acceleration down. So that works for this direction. Notice I don't just ignore units, right? And just leave them off. So equations that you have are the basic ones so far, where V bar is, and remember you can write down the equations on your packet, which will be available for you on the test. So this might be worthwhile to do, and make sure you save it. V bar is delta S over delta T. We know A is delta V over delta T. We know V bar is also VI plus VF over 2. We also know delta V is VF minus VI, and we also did this one, VF equals VI plus A delta T. Okay? So that's what we've used so far today. The next problem says, let's see, is it anything different? It's pretty similar. So let's go to section 2.3. Now what changed in 2.3? What changed there? Right, just the relative amount of dropping. So let's do, well, we'll do a little demo first here, okay? So for this demo, we need a timer. Oh, I put them all in these things, so we get, oh, here's one. Yeah, you can. Let's see how long it takes for this ball to drop 2.7 meters. And I say that because if you go out to the roof and drop the ball down, it's 5.4 meters, if I remember correctly. So we're going to do half of the distance to the ground, 2.7 meters, and I'm searching for a meter stick. So what would be pulling this down? Right. And we would know, so 2, might have to get up on here. Doesn't have to be exact. I'm going to need, maybe Caroline, you can help me here. Okay, I got the spot. Approximately here. Get the timer. Figure out how it works. See how it works? You're going to hit start when I drop the ball. You're going to watch it. And you're going to hit stop when it hits the ground. Okay? It's very important that you're as accurate as possible. Now, if I was doing this in a lab, I would take multiple data things, right? You ready? I'm going to drop it. I'll say 3, 2, 1, and then drop it. 3, 2, 1. Huh? What you get? Let's see. No, 0.65 seconds. Well, actually, that's 65. Yeah, that's 0.65 seconds. So to go 2.7 meters is 0.65 seconds, right? If we found the average speed of that, it would be 4.15 meters per second. Okay, so now if I go out, Michael, you can run downstairs and go outside the door. That door. Now I'm going to drop the next one from out there, okay? That I should have had you, you know how to use it. But he could throw it up if he'll probably mess it up. Outside. If I drop it double the distance, what should happen to the time? The time should double. Okay. Well, let's see if that's true. Come with me to the green roof. I wonder if it's where.